Hello, everybody. Welcome to our second lecture of the first week of our course on AI for Earth observation. In the previous lecture, we got a bit of idea about different types of remote sensing sensors. We also talked a bit about the other possible data that we would probably fuse with remotely sensed images in our Earth observation problems. Towards the end of last lecture, we started talking about different application varieties that probably we would be dealing in Earth observation, and we talked briefly about this particular case where we are interested in tracking the urban green of a city. And then we talked about this particular application where the city authority wants to detect the informal settlement, and we at the end of the last lecture started thinking about which of these two applications would require higher resolution. Think about this to distinguish between the different urban structures which is needed in the second problem to distinguish an informal settlement from otherwise more formal settlement, the kind of features that needs to be captured that would certainly need higher resolution images. Moving forward, now take this example where, let's say, we are talking about this bank which has given some loans, let's say, to some construction projects. So when such loan has been given, let's say the bank was also given a timeline that the development of the construction project will follow this particular schedule. Naturally, the bank would like to keep a track that indeed this schedule is being followed. To do this, here you have to understand the entire process is quite complex. It might be the case that there was already some construction. In that case, there will be a demolition phase. If there was no construction, then of course this demolition phase is not there. However, the construction has started, and let's say at some point first floor has been built, at some point second floor has been built, and let's say like this particular project involves up to 8 floors. So this will go in the phases, and this means this may involve monitoring of, first of all, the destruction of the previously existing construction, and following this, monitoring of features such as height, and thereby we'll need to think which sensor. We'll talk about the sensors in a bit more details later. We need to think really like which sensor is suitable. In this case, can we just use any sensor? Can we use multispectral sensor and hope to, even if it is high resolution, even then, can we just hope that this will work for detection of the height? The answer probably is no, right? So think a bit more about this, and this will become more and more clear in later part of this week or this course. Now think about different disasters that can happen in the urban scenario. So one such disaster that probably happens in most Indian cities is flood. And there, think about to detect this flood or rather waterlogging, do you use just one image or would you use multiple images? Or rather, the question to ask is that can you solve this problem with one image? And is this solution, will it be like a better solution if we rather use two images, or would it be even better if we used even more than two images? And then again, the cross sensor scenario also becomes important, as we had already mentioned before, that in such time series analysis scenarios, probably we are interested to fuse information from multiple sensors. Similarly, another application with respect to the disaster monitoring in the urban scenario is monitoring the impact of earthquake. If an earthquake occurs, many buildings can be completely or partially destroyed. Here again, there are several questions that need to be answered. First of all, again, is it one image problem, or is it two image problem, or is it even a time series problem? Then think of again similarly to our discussion with respect to the when we talked about this bank financing construction activity. In the similar line here, think about, is it the case that given a particular sensor A, okay, this can effectively detect the fully destroyed building? Does that automatically imply that this will also be able to detect partially destroyed building? So the answer to this, think about this in the terms of the characteristics of the sensors. So think like, let me give a bit of like hints here. Think about like, okay, you are talking about with respect to two images, a pre-earthquake image, a post-earthquake image. Even then, like, is the capability of been able to detect fully destroyed building, does it automatically imply the capability to detect partially destroyed building as well? So we have discussed a few scenarios in the context of cities. However, let us now move out of the cities. Let's say, let us take a tour of the forests. Here, one important aspect, and which is, of course, very important in the Indian context, is forest fire. Forest fire is indeed very frequent in the forests in Indian Himalayas, as well as even if we consider the forests in the other continents as well. It's probably not that difficult to understand why, like, once a fire incident starting in a forest, why it would spread quite fast. And we have seen even devastating incidents from developed countries such as US, like most developed provinces probably they are like California and all. Often we see newspaper reports stating about huge fire incidents from those places as well. And this forest fire itself, I mean, there are several sub problems that one can deal, or like researchers actually deal with earth observation data. So one is very straightforward. The forest fire has already happened and like the incident has already completed. After that, the attempt to understand what all has been, which all places have been impacted. So basically the burnt pixels. The another is, given that there is a ongoing forest fire incident, and let's say on today's date the fire is located in this particular area, given this information and given some other background information like local terrain, is there a river present in the area, a lot of other things like that, to predict how the fire will spread and where the fire will spread tomorrow, let's say. There can be also another version of this problem where we are not really talking about like, okay, there is an ongoing wildfire, rather we are talking from like the statistics of the previous incidents and current land cover. We are saying like next year which areas probably like which areas are more likely to see wildfire incident, so that like people can take steps accordingly. I mean, there can be a lot of businesses which take steps accordingly. Like, let's say you are owning an insurance company, and obviously the premium that you would be charging to, like, will be first of all taking the insurance. It could be like in a capitalist scenario, it could be the government itself. Even if the forest is owned by the government, I mean, the government itself is also part of the capitalist scenario, and you are running an insurance company, and depending on how likely you think that this particular locality will be, impacted by forest fire will probably charge similar kind of premium. And one point that probably needs a bit of clarification here is that this is not simply, like you just count, okay, this particular, like, let's say you have 10 localities under consideration at this point. You can say that this is not at all an Earth observation. Like, this is not a problem involving satellite images and all. You can just, these 10 localities, so let us call it locality A1, A2, up to A10. So for each of these localities, so you can think of this like 1 kilometer cross 1 kilometer area, or whatever way you have defined these localities. You can claim that, okay, what you do is you count, let's say, for the last couple of years, how many fire incidents have occurred in each of these. And accordingly, you will say that, okay, like if in A1, more fire incidents have occurred and A10 has seen much less incidents, then this is what it's going to be. But that's not, I mean, that would be true if we were talking about a static world. But we are not talking about a static world. Probably a lot of other things are going on. Construction works are going on. Deforestation due to other like human activities, they are going on, and accordingly, the involved risk that is also evolving. And it needs to be monitored on regular basis. Another interesting application with respect to the forestry is tracking of invasive species. As an example, tracking of Lantana camera or other like similar invasive species which are in a way taking up our forests, and there needs to be a control on this. That's the reason probably the government agencies, the forest service departments, they would be interested in tracking such invasive species. Now, we have already thought about our cities. We took a tour of the forests. Let us also think a bit about the agriculture. Indeed, agriculture is very important for our day-to-day life. And think about a simple problem of, like, let's say we are talking about a particular rural area where there are rice fields, but there are also other kinds of crops that are cultivated. And for some reason, you want the segmentation of the rice fields. This, again, think about what kind of image would be suitable for this problem. Would this be a just single image, mono image problem, or will this be a time series problem? Also, of course, often it happens that particular field is not just used for cultivation of a single crop, rather a combination of crops, and that will mean that this segmentation task becomes also much more challenging, that it will need to consider that, okay, what has been rice field can be some other field, or what you are now seeing as like some other crop is being cultivated maybe rice will be cultivated here in future. I mean, I'm talking about still in the same year, let's say. So this will automatically mean that you will need more than one image to rule out, okay, this particular field is not used for rice at all. Think about the monitoring of the agricultural drought, which is very important. You can think about what type of images might be helpful. Is it again a single image problem or a time series problem? Would you be able to get a proper sense of drought from just a single image? The answer is probably no, right? So this automatically leads us to a time series problem and automatically also brings the other cross-sensor analysis challenges that we have briefly discussed before, and we will be again and again coming back to this problem and some solutions in this course. On the similar line, another problem would be understanding of soil moisture. So this is very much related to the previous problem itself. Now, let us think a bit about the maritime domain. Right now, when we are recording these lectures in 2026, the world is going through a crisis in the form of a conflict between two countries where the importance of maritime domain has become well known to almost all of us. So there, again, very naturally, a problem would be detection of ships. Different government agencies, for several reasons, would like to understand the movement of the ships, and also not just ships in the sense like the authorized one. There are often also like unauthorized, illegal movements also that the government agencies probably would like to monitor. Another problem is whale population monitoring, and this is important in some continents where along the coastal area we see a significant population of whales, which also migrate from time to time. And for, again, related to our movement of the ships, so for convenient movement of the ships, it's important to have a good understanding of the whale population movement. Since there is a collision of whale and the ships, this can be harmful for both sides actually, not just the ship, also the whale. Now, just think about all these application examples of Earth observation that we have discussed starting from the end of last lecture till now in today's lecture. If we think about the different algorithmic challenges involved in this applications, this will be very clear that AI or machine learning is indeed very relevant in all of them. Indeed, most of them involves cross-sensor fusion, supervised classification or unsupervised clustering of data, and several other challenges that can be addressed with machine learning or deep learning. And here, one important aspect that I would like to highlight is that it's not just the case that for these earth observation applications, machine learning or deep learning is helpful, and that's the reason that we are interested in this topic. If your interest rather comes from more from the AI side, you are rather interested to develop, new deep learning architectures, or like you want to work in like one of the more recent AI or deep learning paradigms, which we'll briefly mention soon, you'll understand again that for most of them, Earth observation is indeed a great playground. Earth observation is indeed a great application domain where most of the upcoming AI, ML, DL topics can be applied. And the challenges that Earth observation data presents, that is indeed something very interesting for AI researchers to play around with. So I would call this as a great AI playground. So I will take a couple of examples. Think about the foundation models, which we will be discussing in the last 3 weeks, about 2 to 3 weeks of this course, because we will be starting with the vision transformers sometime around week 10, let's say, and then foundation models, and then the foundation models dedicated for Earth observation. There, one very interesting aspect to understand is that when we talk about the foundation models with respect to the computer vision domain, we mostly talk about image and text used together in a model, the contrastive pre-training done with the image and the text. Whereas the Earth observation, this kind of contrastive training can be done with a combination of sensors of different characteristics, such as optical sensors, synthetic aperture radar sensor, or even if you're talking about just multispectral optical sensors, even there different spatial resolution. So sensor A and sensor B with different spatial resolution, they can be used together in this kind of contrastive pipelines. And thus it becomes much more interesting, and of course you can still use the language as well. We are not saying that okay, in the Earth observation you will not be able to use language. You can pretty much use language here as well. On the top of them, there are those additional challenges. If we think about the data security and the privacy domain, again, we'll understand that how strongly relevant this is for Earth observation. In the Earth observation, there are so many space agencies and even private players and often they want to share data only up to a restricted amount of level. So this means the privacy aspects and even the other kind of like the learning aspects that arises out of this, like federated learning and all, they are very relevant in the context of earth observation. Similarly, if we think about the cloud native applications, this is also very strongly relevant for earth observation. With this, we'll end our lecture here today and we'll take forward our discussion in the next lecture. Thank you.